So this will be the assignment 5. Now in the assignment 5, what I'll be discussing is I'll be discussing about first of all the rotating magnetic field. Like you see in the last class we discussed one question related to rotating magnetic field in which the answer was like this, that if you see we discussed in last class this question, right? This is a very interesting question and its correct answer is 0 only. Okay, I checked it again. So what will happen if you talk about only so I'll discuss this right now, that if we talk about only single, if you give a single phase supply to a single phase winding, then for only one winding it is pulsating but not rotating. But if you take all the three phases together, in general what happens that it becomes sinusoidal and rotating. However, if you give so let me just again admit. Okay, however, if you give this, what you say, this kind of, if you give same supply, okay, same supply to the three phase distributed winding, the what you say resultant air gap flux becomes 0. Okay, but if you talk about only single phase, then for a single phase you will see that if for a single phase if you give only single for single phase winding, it will be pulsating but not rotating. So you'll be seeing all these discussions in more detail in this class, and then we will be seeing induction motor. Okay, so we have lot of things to discuss this class. Okay, so let me then start discussion. So again this problem has started. I don't know what is this problem. I'll have to again open this up. Okay, so let us now start. So here you see, if we have in the stator this, so these are from the sir's lectures only. So I have taken some screenshots and I'll be discussing these things. Okay, so that you can relate it to the sir's lecture also. So here you see that in the stator, what, let us say that we have not let us not talk about right now rotor and stator. Let us see that if suppose you have a three-phase distributed winding in space. Okay, so if suppose you have three-phase distributed winding in phase and you are giving the three phase balanced currents in time. Okay, so there are some things. So one thing is that things to note. You have three-phase windings distributed in space, which we have seen in our earlier classes, right? In our earlier classes, we have seen that if we talk about suppose stator of a synchronous machine or induction machine, so it is like this, right? We have slots in the stator, so it is like this. Hmm. So let us say this is the stator, okay? Now in this stator, let us say this is one slot, okay? So in this stator slot, it is like this. Now in this stator slot, what we have is we have three sets of windings. Okay, one for R phase. So let us say this is for R phase. So you have some number of windings, like so number of slots. It can be multiple slots, multiple multi-coil kind of what you say multi-layer winding, right? Then you have Y phase, and then let us say you have B phase. Okay, so how these R phase, Y phase, B phase, and slots are put, that if you see overall over the whole stator, like all the 360-degree of the stator, if you see, then you will see that the distribution of windings is like distribution of turns is like this. Okay, distribution of turns in the slot. So you will see it will be like sinusoid. Okay, so but remember that this is the what you say turns distribution. Okay. So this is the turns distribution, remember. It is given in such a way that if you pass a DC current through these stator windings, suppose in RY, IR, this IR, IY, IB, if you suppose let us say make DC, Then what will happen? For DC current also you will get an AC MMF. Okay. So you will get for DC current also. So let me write it. Okay. That for DC current also, due to this distribution of turns, which is sinusoid, you will get a sinusoid MMF. Okay. This you have to understand. Okay. So, so the turns distribution is such that for DC current also, you will get sinusoidal MMF. So this is what I mean by three-phase windings distributed in phase. Means this turns distribution, like you keep the number of turns such, like let us say we only focus on R phase. But remember that there will be RYB phases in all the slots. Okay. So if I talk about, let us say, only R phase in these slots, so it will be like this. In one, suppose let us say this is like, so this is like, say let us say this is this corresponds to one turn. Okay, this corresponds to two turn. So let us say this has only one turn, then beside this it has two turns, then again besides this it has like three turns. Okay, do you understand? Like this, so you can increase the number of turns of a coil. Basically turn is like this, right? Single turn. So you can make this double turn or something like this. You can make it this multi turn. So this is the turns distribution. Now turns distribution is in such a way that you have so this is what is called as distributed in space. It means that this distribution of the turns is in such a way that even if you give it a DC current, you will get the sinusoidal MMF. So in this picture, that is what sir is talking about. He's saying that let us say you have these three-phase distributed windings in space, and you are giving, let us say, IR, IY, IB. Now let us focus on only one phase. So if you only focus on one phase, that is R phase. Now in R phase, let us say you give DC current. So because of the DC current, you will get this sinusoidal MMF. Okay. Let us say for the first case, you get sinusoidal MMF like this. Now, in the second case, if you make it half, like IDC by 2, then what you will get? You will get again MMF, but it will be half. Okay, the peak will be half, but it will still be sinusoid because of the turns distribution in space. So, do you understand that even if you give DC current, because of the space distribution of the windings, this MMF is sinusoidal. Okay, remember this. It's very important to understand this. Okay. So here what is sir wants to say is that in if suppose you instead of DC you give AC, let us say in the R phase you are giving AC, then what will happen? So what will happen? So let us say for let us say corresponding to I max, you will get first this maximum of MMF flux. Then again, if suppose I max becomes half like this, then you will get again this distribution like this. Then so again, if you make I max again smaller, then it will become small. And if suppose you make Imax negative, then it will change its direction. Okay, it will become negative here, it will become positive here like this. So this is called as pulsating. Okay, so what is happening? So it is happening like this, that depending on the instantaneous value of this I of t. So I of t can be, let us say, I of t in some cases I max. I of t is I max by 2. I of t is minus I max by 2, and I of t is minus I max. So corresponding to this, we are getting this kind of MMFs. So here you can see that this happens automatically because you are giving sinusoidal, right? So because you are giving a sinusoidal current, so because the sinusoidal current magnitude is continuously changing, the instantaneous value is continuously changing. So what is happening? This Bmax waveform is sinusoidal, but it is changing its magnitude continuously. So what is happening? This is called as a standing pulsating wave. Now, if in this previous question, um, this question, if let us come back to this question, if they ask that if all the three phases of this machine are connected in series and then fed from a single phase AC supply, then the air gap flux corresponding to phase A will be. If it is corresponding to phase A, then it will be pulsating but not rotating. Okay, for individual phases, it is pulsating but not rotating like this. From this discussion, it is like, so standing means not rotating. Okay, not rotating, pulsating wave. But if you, so now we will see in our next discussion what happens. Okay, but if you take a sum of it, then let us see what happens. Okay, in the case when you are giving it a so here another thing I want to write. Again it is gone. Okay, so now what we will do is, to these three phase windings distributed in space, you will give, if suppose you give three phase currents distributed in time, then what happens? In that earlier question, so in that earlier question, I'm not going there, but in the earlier question, they gave single phase current to all three phases. Okay, but here uh, in previous assignment I'm writing so that there is no confusion. Okay, but generally this is what is done. You have a three phase windings distributed in space and you give three phase currents distributed in time. Okay, then what happens to the resultant air gap flux? Then we will see a special case, which is this. Okay, that what is this is one special case to this. Okay, so now let us come here. So mhm. So let us say now what we are doing. So as I said earlier that now we will give three phase currents distributed in time. So these are the three phase currents which are distributed in time. So you can see that cos omega t, then there is a 120-degree lag because of the distribution in time, three phase balanced currents. Three phase balanced supply current means they have the same magnitude Imax, but there is a phase displacement of 120-degree. Okay, so this is what is called as three phase currents distributed in time. Okay, this is what I mean by distributed. Okay, so this is the thing. Now what will happen to the resultant mmf? So let us see. So you see the expression of the mmf is like this. Okay, so expression of mmf is like this: ns ir by 2 cos theta. Now this cos theta is coming because of the distribution in space. We can see that this is theta. Okay, this is basically theta. So we can see that when the theta varies, even though if you give DC current, you get the sinusoidal MMF. That is why if you place in the place of IR, you place IDC. Because of this theta, you will get a sinusoidal MMF. Okay. So this is expression of MMF. So I'm writing for all the phases. Okay, ns by 2 is basically the turns. Okay, you this I'm taking from PC cross, this kind of terminology, but you understand this is basically mmf is what number of turns into the current which is carried, so that is the mmf. But now because of the sinusoidal distribution in space, what happens is that you get a, so this is the fundamental component, this cos theta is the fundamental component due to that sinusoidal distribution in space. Okay, so because of this sinusoidal distribution in space, you will have third harmonic, various harmonics. Okay, but we are, so by writing cos theta only, I mean to say only the fundamental component in of the sinusoidal, the distribution, space distribution. Okay, So here that is what sir has also written. So sir has written that okay, so this is your current. So instead of this current IR, you place what you say, let us say I max cos omega t. So N into I max is B max. So B max cos omega t cos theta. Then again you instead of IY, you place what you say I max cos omega t minus 120. So BY becomes B max cos omega t minus 120 and cos theta minus 120. Then what about B phase? B phase also you instead of this IB by 2 IB you place what you say I max. So this NS into I max by 2 which is common in all three, which we are denoting as B max, into we have cos omega t plus 120 and cos theta plus 120. So we can see that there is a what you say, so here this is why we were getting here a pulsating thing. Okay, so if you see the individual phase, so individual phase is cos omega t cos theta, which is pulsating. Okay, so for a single phase it is standing pulsating wave. Okay, the resultant mmf in for the single phase. But let us see what is the resultant mmf for all the three phases taken together. Okay, so if so, what will be the resultant MMF, or the what the air gap MMF produced? Okay, so what we will do is we will add all the three MMFs for three phases. Okay, so if you add it, so if you apply your cosine, what you say identity, that cos A cos B is what? So here cos A cos B is 1 by 2 cos A minus B plus cos A plus B. Okay, so you apply this identity. So this identity has sir has also applied. Okay, so you put this identity into place. So you have cos sum plus cos difference, then again cos sum for these two plus cos difference for these two, and again cos sum plus cos difference. Now what is happening? Because you see here you can if you take the sum of these three na, so this is like this. If you anytime see a sum of like this, cos theta plus cos theta minus 120 plus cos theta plus 120. So if you simplify this, so you will see this will come out to be 0. Okay, so you can see from the identities. Okay, so here also this is the same thing, but instead of theta we have omega t plus theta. Omega t plus theta is common in all the three, so omega t plus theta minus 240, which is plus 120, and omega t plus theta plus 240 is minus 120. Okay, so this comes out to be 0. So what you are left with? You are left with only these three. Okay, these three are the same thing, so you will get 3 by 2 b max cos omega t minus theta. So you are getting something like this. Okay, so this is the resultant air gap MMF. If you give three phase currents, balanced three phase balanced currents means they have same magnitude but they are phase displaced, two three phase distributed windings, so you get resultant MMF like this. Okay, but if you give the same currents, like suppose let us take the case where you are giving the same current. Okay, so I'm which was the question in the last class. Okay, so I'm just including that slide here. So let us say that in the question it was said that all the three windings you are connected in series, and then you are giving it the same current. So let us say you are giving it same current as same single phase. So let us say you give only I max cos omega t to all the three phases. Then what happens? Okay, so let us now again, so we know that the expression of MMF is what? So MMF of A phase is some terms ns by 2. Okay, so I max I'm not writing, I'm just writing IR. Okay, because that is what we wrote in the last thing. ठीक है, IR cos theta, MMF B is ns by 2 IY cos theta minus 120, and MMF C is ns by 2 IB cos theta plus 120. So now what we will do, we will add up these MMFs, and remember this IA is same in all the three phases, which was the question. Okay, so this was the question. Last assignment question. Okay. So what will happen? So let us see the resultant MMF. So resultant MMF is what? MMF A plus MMF B plus MMF C. Okay. So this will be NS by 2. Okay. IR is same for all, which is the same thing. So I'm writing it as IA cos theta plus cos theta minus 120 plus cos theta plus 120 because IR is equal to IY is equal to um, IA. So I'm writing like this. Okay. So this is the thing. Now, as I said, the identity is like this that cos theta can be omega t also. Okay. It can be any angle. So so identity, so I'm writing it like this. So identity I'm writing in other color. So trigonometric identity. So by applying trigonometric identity cos A plus cos A minus 120 plus cos A plus 120 is equal to 0. This is also valid for sine also. Okay, sine A. You can just expand this. You know how to expand it in terms of cos A minus B, cos of A minus B plus cos of A. You know this, you can, what you say, expand this. Okay. So you will see that it will come out to be 0. Okay. So from this, you will see that, mm, so this will become 0. Okay. We get resultant MMF as 0. Okay. But if they would have asked in the question, in the earlier question, that what is the single phase MMF? So if you see across a single phase winding, okay, not the three phase windings together, only single phase winding, then in the single phase winding you will get a non-rotating pulsating wave like this. Okay. But if you take all the three together for that question, you will get it as 0. Okay. So this is from all this discussion. Now let us come back here. So under normal situation, when you give three-phase currents which are distributed in time to three-phase windings which are distributed in space, you get a resultant MMF like this. Okay, so like this. So now from here, so so this is like this. So this is what sir has also written in his class. He also got the same thing. Okay. So here if you see that, so what is happening, so let us say at omega t is equal to 0, this is, so you have this expression. Okay, so at omega t equal to 0, what is this? This is 3 by 2 b max cos theta. Okay, then suppose what happens, so you make omega t as pi by 3. So what is happening, it gets shifted like this, it gets shifted towards this side. Okay, so you can see that it is getting shifted towards this side as you are changing omega t. So what does this means? It means that the resultant air gap MMF is nothing but it is a sinusoid, but it is rotating sinusoid. Okay. So it is a rotating sinusoid MMF. And what is the speed of the rotation? It is nothing but the speed corresponding to this omega t, because as this omega t is changing over the 360-degree, that is, so with what speed it is changing, so you will see that the frequency of this rotating sinusoidal MMF is omega t. So if someone asks you what is the frequency of this, so this is omega. Now remember, so omega t ni, because I'm talking about frequency, so this is omega in radian per second. Okay. in radian per second. ठीक है? So that is the thing. Now, so this is what sir is also trying to tell you people that okay, so what is happening as you keep on changing omega t, so b resultant is 3 by 2 b max cos theta, but at omega t equal to pi by 3, it gets shifted like this. Okay, it gets, because theta minus pi by 3 means it is getting what? It is lagging, right? So it is becoming lagging. So that is what is happening. So if this omega t goes from 0 to 360 degree, so what will happen? This sinusoidal will be continuously shifting and then coming back to its original place. So what is happening? It is rotating in the stator. Okay. So this is what Sir is trying to prove now mathematically. So what is happening to the magnitude? So if suppose let us say you take omega t is equal to 0. So if you take for omega t is equal to 0, so what will be the instantaneous values of currents? IR, IY, IB. So you will get IR, if you put omega t is equal to 0, you will get plus I max. IY you get minus I max by 2. IB you will get minus I max by 2. Okay. So what is happening? So this is your, so this is so this is R phase. Okay. So hmm. So this is Y phase and this is D phase. Okay. So here, so why I said this is because you see, so we generally take our phasors to rotate in this direction, okay, anti-clockwise. Now first the R phase will come at this position. If suppose you are standing here and this is rotating, so first R phase will come, then Y phase will come, and then the B phase should come. Okay, so like that I have drawn the phasor. So in this phasor diagram, if you put it like this, let's suppose your IR is plus Imax. So I'm from this phasor I'm drawing. Okay, the same diagram I will arrive at. So IR is plus Imax. What is IY? IY is minus Imax by 2. So minus Imax means here this is minus IY. Okay, so this is Imax by 2 because I have already taken minus sign in this direction. So minus sign I'm not writing it again. Then what about IB? IB is also minus Imax by 2. So this is minus IB. So this is Imax by 2. Okay. So, and we know that, so what happens? This whole angle is 120 degree, remember, but because this is coming at the midpoint, so this angle is 60 degree, and this angle here is another 60 degree. Okay. Hmm. Okay, so this is omega t equal to 0. So we are just trying to see what will be the magnitude, overall resultant MMF magnitude at omega t equal to 0. So if you keep in the current expression omega t equal to 0, so IR cos 0 is IR equal to like that, like that. Huh? And then IY, if you put cos of 120, then it becomes minus I max by 2, and again cos of plus 120 also minus I max by 2. Okay, so like that. So I'm just trying to, so why I'm telling this thing is so that you can relate it to sir's lectures, because see my class is like only like about very less time. Okay, but if you will see the sir's lectures, it is equivalent to like 5 hours. Okay, for 1 week. So I just try to cover the gist of the things. I cannot, so that is why I'm just trying to tell these things so that you can understand what was sir discussing. Okay. Okay. So here, if you see, so in his sir's discussion, that this is how he has arrived at this expression. Okay, so this, because this Imax is proportional to Bmax, so he has replaced Imax by Bmax by 2. Okay, like that. So what is happening? So if so earlier was there any doubt in the earlier discussion? Till now it is clear, right? Actually this is very interesting. Okay, this thing, pulsating thing, this is like very interesting. So if you understand this, and if you understand how this rotating mmf is produced, then it is very interesting. Like if some kind of theory questions come, you can tackle that. Okay, they may twist it around, but you can tackle it. Okay. So like that. So now, so here coming back here. So so I'll open it again because I know I'll have the same problem again. Okay. Hmm. So, so what I'm trying to do is I'm trying to do the corresponding phasor. So this is R phase, Y phase, B phase originally, but because here this IR is plus Imax, so it is in this direction in along IR, and IY is minus Imax by 2, so it is along minus IY, which is 60 degree from R phase. Okay, minus IY 60 degree from R phase. Similarly, minus IB is 60 degree from R phase. So that is why sir has also marked it as 60 degree, 60 degree. So this is B max by 2, B max by 2, because that is what we have gotten in magnitude. So direction of the phasor is like this and magnitude is half. Okay, B max by 2, B max by 2. So if you take the component resultant along this, so what it will be, it will, if you see, so it will be, so you can take the component along this, so so it will be what, b max by 2 into cos 60, and that 2 into 2. Okay, so if you add it up you will get 3 by 2 b max. So this is like this, that so this is b max and then b max by 2 cos 60 and then b max by 2 cos 60. So you have 2 b max cos 2 b max by 2 cos 60. So 2 cancels and cos 60 is 1 by 2. Okay, so cos 60 is 1 by 2. So 1 by 2 plus 1 is 3 by 2 B max. Okay. So you will see that if you take omega t equal to 0, omega t 30, omega t 60, omega t 15, omega t 5 degree, whatever, your resultant MMF, so your resultant MMF magnitude remains 3 by 2 B max. That is what sir was trying to say. That magnitude remains 3 by 2 B max only. Okay, of the resultant MMF. So here also again sir has found this for omega t is equal to 30. So here what is sir trying to do? Sir is trying to again prove that how, so here in this discussion what he is trying to say the same thing, that this is a rotating MMF, which you can understand, right? So this was 3 by 2 b max cos theta, but as omega t becomes pi by 3, it gets shifted by 3 by 2 b max cos theta minus pi by 3. So it gets shifted in by pi by 3. So how it is shifting? It is shifting as the omega t varies, right? So how what, so at what speed this shifting will be dependent on? This shifting will be dependent on omega speed. So that is why the this rotation, this frequency of this rotating mmf is omega. Okay, so this is what sir is also trying to prove mathematically. I'll not go into this, okay, but this is the gist of the things he actually told once here, and then he's trying to derive it mathematically, that okay, if you, but it is the same thing. Okay, if you understand this pictorially, then no need to go into that much maths. No one will ask you this much of maths. Okay, the proof of that. Okay, so like that. So so in resultant what you have is that the magnitude of this remains 3 by 2 b max. So this resultant air gap flux magnitude is 3 by 2 b max. Okay, but how it is rotating? It is rotating with omega, the speed in electrical radian per second. Okay, so remember omega is electrical radian per second. Okay, so that is important. Okay, now let us come to induction motor. So how to apply this discussion in induction motor? Okay. So here also what we are doing, we have the three phase distributed, three phase windings distributed in space, and we are giving it a what you say balanced three phase supply R by B having the supply frequency F. So what will happen? So we can see that the rotating magnetic field will be produced, which will have the peak of 3 by 2 B max, and it is rotating with a speed, you can see it is rotating at the speed of 2f by p rps, and in rpm it is the very famous expression like this. So ns, so ns here is 2f by p rps, and ns is also 120 f by p rpm. Okay, so like this. So here if you see this is, so it is rotating in 3 by 2 b max direction, but if suppose you reverse the supply, okay, so instead of if you exchange these two phases, let us say in this case, so let us say you are giving y phase to so I you are giving IY to B phase winding and you are giving IB to Y phase winding, then you will see what will happen. So the speed will remain the same, magnitude of the speed will remain the same, but this MMF will start to rotate in opposite direction. So MMF you will see rotates from leading phase in time, remember, to lagging phase. Okay. So you see here, so here you see, so we know that what is the leading phase. So first we have IR, I, IR, IY, IB. Okay. So you remember I'm denoting IR, IY, IB, which means I'm talking about the supply. Okay. I'm talking about the supply phase sequence. So supply phaser. So we anyway know that the distributed winding phaser is also like this, but I'm talking about supply phaser. Okay, so supply phaser is varying in time. So this is in time, and winding is in space. Okay, winding is in space. Winding distributed in space, and supply is distributed in time, phasor. Okay, so this is the phasor diagram, but here what is happening? So r phase winding is getting IR. Okay, that is remains the same, but B phase winding now is getting IY. Okay, so I should not draw it like this because it will be confusing. Okay, so you see, so what will happen? So in this case, you see, first R phase was there. We know that what will be the so as I said, MMF rotates from leading phase to lagging phase. We know that this is the phase sequence in time, right? First IR is there, then IY is there, then IB is there. Because IR is what? So we know that IR is I max cos omega t. IY is I max cos omega t minus 120, and IB is I max cos omega t minus 240, or cos omega t plus 120, same thing. Okay, so like this. So we can see here that R phase, first R phase is coming, then after 120 degree there is same thing is repeating at Y phase, and then again after 120 degree 240 degree, same thing which was happening at R phase will come at B phase. Okay, so this is the so this is, you can see that the supply is what you say, so supply leading phase is R phase, then then Y phase, then B phase. Okay, so this is this is what I mean by leading phase in time. So leading the most the what so the in the, so in time phase sequences R Y B. So what we have done, we have given R phase here, but Y phase we are giving here. So what is happening? So in this case, R phase is here, then Y phase is here. So what will happen? Okay, so MMF will first go to R phase, then from R phase it will go to Y phase, and then from Y phase it will go back to B phase. Okay. But here you see, this was what was happening. But here what is happening? Y phase is going to the B phase winding. So what is happening? We have to see, okay, where is the Y phase in time? So Y phase in time is now here. So what will happen? This rotating MMF will first start from R phase, because R phase is still the same, but this B phase winding is getting Y phase current. So what will happen? It will go to Y phase, because Y phase current is in time, which is leading, right? Leading compared to B phase current in time. So that is why first it will go to Y phase, and then it will go to what you say, B phase in time. So that is why it will it so this MMF rotates from leading phase in time to lagging phase in time. Okay, so I hope this, so this, in this way you can visualize that, okay, how the mmf is rotating. Okay, this sir has also, I don't know whether he has proved it via some mathematics, but this is the gist of the things, like how the mmf rotates, in which direction you can predict mmf rotates depending on this three phase supply. Okay, so now let us say that you have the stator winding like this. Okay, so this is the stator. Now let us suppose the rotor is also rotating. Okay, so what will be the induced EMF in the rotor? So induced EMF in the rotor will be root 2 pi into this flux per pole phi, which we have seen, right? This we have seen. So here we were writing directly frequency earlier, but we will not write the frequency. We will write it in terms of speed. So what is the relation between the frequency and speed in RPS? So this is the relation. Okay. Okay, so one thing is that in my place there is some storm. Okay, so at any time the power may go. So what I'll do is, if power cuts, then I'll save it till here and upload the video till whatever I have discussed right now in part here. And what I can do is I can take the class again at the same time tomorrow. Okay, the remaining part. If the power cuts, power goes off. But if the power does not go off, then we can continue normally. Okay. I'm just telling you in advance. Okay, I'll upload this video, but if the power cut happens, because earlier also there was a storm and the power cut was there for a very long time. Okay, so if I'm not able to continue the class, I'll continue the discussion tomorrow at from 5 p.m. Okay, and then I'll upload that video. But right now, if there no power cut happens, I'll continue like that. Okay. Okay. Today when you also discuss the assignment problem, no, I'll discuss the assignment problems. Assignment problems are very easy. Okay, if you understand these things, it is very easy. Like you will solve very easily. Okay, so I'll just if there no power cut happens, I'll finish it off today only. Okay, okay, okay. So coming back here, so this is the relation between the, what you say, frequency and speed in RPS. Okay, so here also, if suppose if we talk about E1, so if I write E1, so E1 is this. We have seen it in the last class. Okay, this we know very well that this phi is flux per pole. Okay, F is the frequency. Now instead of F, I can write it as like this, because ns is 2f by p rps. So if I write it in terms of rps, it will become like this, root 2 pi, and this becomes uh, p into ns by 2 phi k omega n1. Okay, so this is E1 in terms of speed in rps ns. Okay, now here what will be the emf E2? So EMF E2 is what? EMF E2 is nothing but what you say. So let us say that this rotor by hand is rotating at speed nr. Okay, I'll discuss how this rotation happens, but let us now assume that rotor is rotating at nr and your stator mmf is at ns. Okay, so what will be the emf induced in rotor due to the stator mmf? So we know that the expression, because this emf expression is coming from blv, where b is the relative speed, right? So relative speed between the mmf and the and this rotor speed is what? Ns minus nr. That is why in this expression, this root 2 pi remains the same, flux per pole remain the same, k omega remains the same, and p by 2 remains the same. But instead of ns, I'm writing it, sir has written it as ns minus nr. Okay, because why the emf is induced? Emf is induced because of the because either due to the, what you say, because there has to be a relative change in mmf, relative change in flux. So what is the change in flux here? The change in flux is in what you say motion, right? Because when we talk about generators, motors, DC machine, induction machine, synchronous machine, or in all these machines, you are what you say what you're doing. Either the flux is rotating, either your in the DC machine case, what is happening, permanent magnets or in electromagnets in the rotor is made to no, rotor is stationary but armature is rotating, right? So what happens that in so flux line, so windings have to cut the flux lines. So here the windings of the rotor are cutting the flux lines, but at what speed? Because this is at nr, this mmf is at ns. At what relative speed the rotor windings of this rotor is getting cut by the magnetic field? It is ns minus nr. That is why in the E2 expression you have root 2 pi p into ns minus nr by 2 phi k omega n2. So E1 is this, E1 is root 2 pi p ns by 2 phi k omega n, and this is ns minus nr. Now I'll introduce something called as slip. Okay. So slip is what? So slip is ns minus nr by ns. Okay. So here instead of ns minus nr, I can, so this is, I'm noting it's s. Okay. So instead of ns minus nr, I can write it as sns. So here I can write it as sns. Okay. So this is root 2 pi fp sns by 2 phi k omega, and let us say this n1 and n2 we make the same. Okay, let us say that n1 and n2 in the terms of this stator and rotor becomes the same. Let us say this is same as n1. So this is n1. So you can see that this is what? This is s into e1, slip times of e1. So this is what? Root 2 pi p ns minus nr I am writing as sns. So sns by 2 phi k omega n. And if we say, let us say that the number of turns in the stator and rotor is same, so this is n. Okay. Now here we know that E1 is root 2 pi p ns by 2 phi k omega n. So here I'm replacing this root 2 pi p ns by 2 phi k omega. So I'm left with SE1. So E2 is slip times of E1. This is what happens in the induction machine also. Okay. So there are multiple questions. So I'll just go to some set series of questions. Okay. So I'll come back again here, but these are related to that. Okay. So in these questions, it is said that so the stator of this, so this is the stator of a 12-pole three-phase induction motor, which is excited from a 50 hertz supply. The stator field is rotating in the anti-clockwise direction with respect to a ground observer. Okay. The rotor is open circuited. The RMS value of the phase voltage induced in the rotor is 240 volt when the rotor is held stationary. Okay. And remember, when the rotor is held stationary means what? If you're if so in this thing, if nr becomes 0, rotor is stationary means nr becomes 0, then you will see that E2 will come out to be same as E1. Because if your rotor is stationary, then this nr is 0, then what happens? Slip becomes 1. So E2 will become same as E1. Okay, so that is what they are trying to say. So I'll again maybe put a slide here because it is very messy. Okay, so I'm writing the things clearly here. Okay, first thing is slip, which is ns minus nr by ns. E1 is root 2 pi, first of all, f phi k omega n, n1, let us say. Okay. And this can also be written as root 2 pi f. This is an f name, p ns by 2, because we are replacing f by p ns by 2 phi k omega n1. E2 is what? E2, when rotor is rotating with speed nr. Okay, so E2 becomes root 2 pi f2 pi k omega n2. Okay, This is root 2 pi f p ns minus nr, okay, by 2 phi k omega n2. Right. Now, if suppose when rotor is stationary, okay. So in this case, we are talking that, okay, let us say this rotor windings are open, they're not closed. Okay, so this is the induced EMF which will happen. Okay, so when rotor is stationary, so NR is 0. So E2 becomes root 2 pi P ns by 2 phi k omega n2. Okay, so this is what happens. So here, this is what this is. So this is E2 rotating, E2 stationary, and what is this ns minus nr by ns is slip. Okay, slip is equal to s. So here I can write E2 stationary, so E2 rotating is root 2 pi p ns minus nr by ns. So this is ns into by 2 into slip into phi k omega n2, which is slip times E2 stationary. Right. So this is what is happening. So this is E2 rotating. Why this E2 EMF was induced? Because of the relative speed difference of this rotor and this rotating magnetic field. So what is the relative speed difference? It is ns minus nr. So that is why this EMF was getting induced here. For the EMF induced in the stator, what is happening for the stator? It is ns only because it is stationary. Stationary means what will be the relative speed? So relative speed for the stationary will be ns minus 0 because stator speed is 0. Stator is fixed in place. That is why for the E1 it is like this, root 2 pi p ns by 2 phi k omega n1. And if the rotor is stationary, let us say nr is 0. So for this also, this relative speed difference will be ns only. Right. So that is why root 2 pi p ns by 2 phi k omega n2 when the rotor is stationary. Okay. So these sets of questions are related to this. So you have to remember this, okay, that E2 rotating is equal to slip times E2 stationary. Okay. So first 4 5 questions are this only. So let us just see those questions, okay, so that you can just quickly. So is there any doubt here that how this is coming? Is there any doubt here? No, right? What about the other lady who is here? Is there any doubt? Shivangini? So if there is any doubt, so let me know. Shivangini, do you have any doubt? Okay, okay. ठीक है. Okay. So now let us now start. Again, this issue is happening. So let me open this up. Okay. So now we will see the questions. You will just see that we have to apply this formula in these questions. Okay. So here you see, so they are saying that this stator of a 12-volt three-phase induction motor is excited from a 50 hertz supply. Okay, so from this what we know? We know that we can find out ns because we have the supply frequency. We know number of poles, so we can find the speed in RPM. So what is the speed in ns in RPM? It is 120 F by P in RPM. Okay, or it is 2f by p in rps. Okay, but we will just take RPM because here you will see in the question it is given in generally RPM information is given. But why we took this RPS is because we can easily substitute in the place of in this expressions we can write in terms of NS NR in RPS very easily. Okay, that is why because here then there will be instead of 2 there will be 120, right? A big number. So that is why they did everything in RPS, but it is valid still for RPM also. Okay, all this discussion. So here, coming back here, so this is like this 2F by P in RPS. Now what we will do, we will find the synchronous speed. So it is 120, frequency is 50 hertz. So frequency is 50 hertz. And what is the number of poles? Number of poles is 12. So if we do this, we will get 500 RPM. Okay. So see, stator field is rotating 500 RPM in anti-clockwise direction. In anti-clockwise direction. Because they have mentioned that the stator field is rotating in the anti-clockwise direction. So I'm just writing this. Okay. And they are saying that by some external uh, so rotor EMF, if the rotor is held stationary, so E2 stationary, it has been given as 240 volt. Now what is being asked? It is asked that if the rotor is rotated by some external means at 500 RPM in clockwise direction, though this is important, okay, clockwise and anti-clockwise. So NR is 500 RPM in clockwise direction. So what will be the stator in so what will be the rotor voltage induced? Okay, so what is this E2 rotating for this speed? Okay, 500 RPM in clockwise direction. So we know first of all this is slip times of E2 stationary. We know this from our discussion here, right? This one from this discussion. So here So here we have E2 rotating as slip times of E2 stationary. Now, what is the slip? That is the question, right? So slip is what? Slip is Ns minus Nr by Ns. Okay. But remember, let us say that we are taking the anti-clockwise direction as is our reference. Okay. So Ns is rotating like this. Nr is rotating like this. So here it will be like this. Okay, so let us take it as anti-clockwise. Okay, so all of this we have to take in anti-clockwise direction. So slip will be what? It will be ns, anti-clockwise direction is 500 rpm. But what is nr in anti-clockwise direction? Nr is 500 rpm in clockwise direction, then it will be minus 500 rpm in anti-clockwise direction. Opposite, right? So that is why we have to take minus 500 by 500. So you will get slip as 2. So what will be the E2 rotating? It will be 2 into this E2 stationary 240 volt, which is 480 volt. Okay. Is this question clear? You just have to see this clockwise and anti-clockwise very carefully. Okay. If you just think, okay, this is 500 RPM, then you take it as 0, then your answer will be wrong. So you have to very carefully, you have to notice that is there any direction mentioned? Okay, like that. Now here you see now they are saying that NS is we have found out NS from this, right, in the earlier question for the same data. NS is 500 RPM in anti-clockwise. What is NR? NR is now they are saying 500 RPM in anti-clockwise. Okay. So E2 stationary is 240 volt. Now they're asking us E2 rotating. So this is slip times of E2 stationary. And what is the slip for this case? Slip is ns minus nr by ns, which is 0 because this is 500 rpm in both the same directions, right? So this is 0. So what is this E2 rotating? It is 0 volts. Okay, this is the answer, 0 volts. Now again, they are just changing this speed. Okay, they are once making it 350. Now they have made it 350. But so here again, what they are saying that okay, now this 5 and ns is 500 rpm in anti-clockwise. Now nr is 350 rpm in anti-clockwise direction. So what is your slip? Slip is ns minus nr by ns, which is 500 minus 350 by 500. So you will get it as, so what you will get? You will get, I guess, 150 by 500. So which will come out to be as 0.3. Okay. 150 by 300. So you'll get it as 0.3, which I'm taking from here also. Okay. Now, you just have to remember that E2 rotating is slip times of E2 stationary. So this is 0.3 times of E2 stationary, which is 240 volt. This is 72 volt. Okay. Again, the next question is the same, but here just see that. Okay. So let us see now. So here we have NS as 500 RPM in anti-clockwise direction. NR is so now let us see the slip. So slip is NS minus NR by NS. So this will be 500 minus 700 by 500, which is like minus 0.4. So E2 will be E2 rotating slip times E2 stationary. So this is minus 0.4 into 240 minus 96 volt. If they ask you to enter a positive number, then you have to enter it as 96 volt. I guess in the question they have asked you to enter a positive number. That is why they have given it as plus. Okay, but this is in negative induced voltage. Okay, like this. So these are some sets of questions which are related to this discussion. Okay, this slide. Now, so this was the thing. Now let us see that how actually this. So here also, sir is again continuing the same thing. Here he have written that okay, E1 is like this, which can be replaced by F. So here you have E1 as root 2 pi F phi k omega N1, which I have written here, right? Root 2 pi F phi k omega kW N1. Then E2 is root 2 pi P ns by 2 phi k omega n2 when nr is 0. Otherwise, it is ns minus nr. But since nr is 0, that is why sir has written this E2 stationary. Okay. So this is what sir was also discussing in this slide. Okay. So now let us so what is happening? So if suppose that so what will happen is that this bs is what? Bs is the rotating magnetic field, right? Now, so this rotating magnetic field is what it is when it comes aligns to this. So let us say this is R phase, Y phase, B phase of stator, and this is R phase, Y phase, and B phase of rotor. Okay. Now let us say that NR is 0. Let us say that by some means we have made the rotor to be locked. Okay, like mechanically locked. Rotor is mechanically locked. So what will happen as this BS is passing this, so BS is also passing through this rotor, over the rotor also. So this, what will happen is that RR will have the maximum MMF when the BS is aligned across this. Then again YR will have maximum MMF when this BS will come like this. And then BR will have maximum MMF when BS will come like this. Okay, like this. So what is sir saying is that so induced EMF depends on where is the position of rotor. Okay, so when this so this BS, when this BS comes in this place, so your EMF will be like, so let us say that you have R phase, Y phase, B phase. Okay, then you have BS like this. Okay, at NS. Now this is stator. Now this same NS, so what will happen? There will be some EMF induced in the stator because of this rotating BS, right? Which we wrote it also as E1, right? We wrote down E1 expression. Sir has also written down E1 expression. Now this E1 will be what? It will be three phase, what you say, voltages. So three phase voltages will be like this: R, E1 R, E1 Y, E1 B. Okay, like this. Now let us say that your rotor is like this. Rotor R phase is here. Rotor Y phase is here. And rotor B phase is here. So what will happen? So because this NS is also, so this BS is also rotating over this rotor. It is cutting also the rotor, right? This flux is cutting the rotor windings. So what will happen? EMF will induced. So how will the EMF induce? So EMF will be induced like this. So this is E2R, E2Y, E2B. So what is happening? There is a phase shift, right? Between the E2 and E1. So here E1 was, E1R was here. So E1R is here. So what is happening? There is a phase shift. So if suppose you make your rotor as locked mechanically, then what will happen? Between E1 and E2, there will be a phase shift. Okay, there will be one phase shift induced like this. So that is what Sir was saying. Now we will see the how the rotor rotates in induction. So let us say that we are not locking it mechanically, but now rotor is free to rotate. Then what will happen? Okay, so let us say that first you give three-phase supply to your three-phase distributed windings in the stator like this. So what will happen? As a result, rotating MMF will be produced in this direction, BS with the BS as 3 by 2 B max, and with the speed of ns in this direction, right? We know what is the direction. It is from leading phase to lagging phase, right? Like that. So it will be rotating in this direction. Now Let us suppose in the in the rotor what will happen, because this, so in the, if suppose in the, so these flux lines are cutting the rotor, so what will happen, E2 will get induced. But but what about the rotor flux? Will there be a rotor flux? So if suppose the rotor is like this, okay, so E2 is induced, but rotor flux, remember, will not be produced unless the rotor current flows. Okay, so rotor flux will not be produced unless rotor current flows. So for making the rotor current to flow, what we generally do, we short circuit it. So when we short circuit the rotor windings, it is called a squirrel cage induction motor. Right. So what happens, that first of all you have north and south pole of, in because of this rotating magnetic field will have north and south pole. So let us say this is the north and south pole of the stator corresponding to that rotating magnetic field. Now because of because of the current flowing in the rotor, what will happen, that okay, someone is asking to join. Let me join that person. Someone wants to join. Okay. Okay. So here, as I was saying, that, so this is the case of squirrel cage induction motor where you have your rotor, what you say, winding short circuited. So what will happen because of this? There will be rotor current. Now what we know, first of all, we know it from the, so we know that first of all, because of this current flowing in the rotor windings, there will be a rotor MMF. So let us, that rotor MMF will also have north and south pole. So what will happen? This north pole will try to attach to the south pole, and this south pole of the rotor will try to attach to the north pole of the stator. But remember that this is moving, right? So because of this movement in the stator, what will happen, this rotor mmf, this mmf will try to move. So in that case, what will happen, this rotor will also rotate. In another way, you can also try to see how the rotor rotates is that what you have, that you have the stator mmf. So let us say this is the stator north pole, south pole. And also what is happening, let us say that you have now the rotor windings which are short circuited and they are carrying some current. But we can find the current carrying, we know that current carrying conductor placed in the presence of north and south pole will experience force, and because of this force it will try to rotate. So we know, so let me just write the sequence of the things. Okay, so first I'll write this, then I'll in the fresh page I will write the sequence of the things. Experience force. So it will rotate because of that force. Okay. So let me just write these things down, the sequence of things in the fresh page. Okay. So that you will understand this induction motor action. So I'm writing it as induction motor working principle. So what you do, you um, supply a three-phase balanced supply in time to three-phase Distributed winding in space. Winding in space. Okay. So supply a three-phased balanced in this is happening in stator. Okay. So this is in stator. As a result, there is a rotating magnetic field in stator having omega electrical radian per second speed. Okay, which we have seen. Which we can see it in the previous slides, right? We have seen that this is the speed of the rotating magnetic field. Now, and which is also given as 120 F by P in RPM. Okay. Now, this rotating magnetic field links rotor windings and induce EMF E2. Okay. As rotor windings are short circuited, there is rotor current due to E2. Now, rotor is carrying current in the presence of stator rotating magnetic field, and hence it will experience force whose direction can be found using Fleming's left hand rule. So this is how the rotor, so these things happen. Okay, first of all, what happens is that you give a three-phase balance supply to the stator, and because it has distributed winding, so what will happen? There will be a rotating magnetic field. And its rotating magnetic field will have the, what you say, the peak value of 3 by 2 B max, and this will be the speed of the rotating magnetic field, 120 F by P. Now, because of this rotating magnetic field, what will happen? This will link the rotor windings and it will induce the EMF E2. And as the rotor windings are short circuited, what will happen? There will be rotor current because of this E2. Now, there is current carrying conductors, right, placed in the magnetic field. What is the magnetic field? It is the stator rotating magnetic field. So, what will happen? This current carrying conductors will experience force and then it will start to rotate. So, in this way, the rotor rotates in the what you say induction machine. So this is what was sir trying to say in one of these lectures. Okay, in this lecture. So now we will go 2 here. So here now we will try to find the expression of torque. Okay, we know first of all that there will be a torque action because of all this discussion. Now what is the expression of torque? Now we will try to see. Okay, so here, so let us see, let us say that here we have, so here let us say this conductor in the rotor is carrying current dot, and this current is cross. Okay, this is cross here in this slot, and this is the dot here in this slot. Now let us say that this is the stator mmf bs, and we know that because in the rotor also, if you have three distributed windings, so there will be a rotating this rotating mmf br in the rotor also. So this br is, let us say, here. So let us say this br is here. Now we know that BR will try to, what it will try to do, it will try to come close to BS. We know that because the North Pole will try to attract South Pole and all that. And also we can find it using this Fleming's left hand rule in these conductor positions also. And then we will see that, okay, this will try to rotate in this direction only. Okay, so you can do it in both the ways. Now here we know that what is the expression of torque. So the expression of torque we know is BIL, right? We have seen this. So so this is BS. Now let us say that this angle between this conductor position and this BS is theta. So the component of BS along this what you say conductor position is what? BS cos theta. So this is BS cos theta, and what is the current which is getting carried by the rotor, conductor? This is IR, rotor current. So this is the magnetic field BS cos theta, B in the place of B, rotor current IR, and this is the length of the, but basically the conductor. Okay, so now this will be the torque experienced. Now you see this torque experienced, we know that this IR is proportional to the mmf of this rotor. This is generally the case, right? The stator current is proportional to the mmf of the stator. So this rotor current is proportional to the stator, the mmf of the rotor. So instead of this, let us say that we have some constant k. Okay, so this constant k, and instead of IR, because we know that IR is proportional to BR, so this k is the constant of proportionality into BR BS cos theta. Okay, but what is this theta? So if you see this theta, what is this theta? Let us say that the angle difference between BS and BR is this gamma. Okay, so let me just erase this. Okay, so this is the thing. So B in the so angle difference between, let us say, BS and BR be gamma. So this theta can be written as what? Because we know that this angle is, so you see, so you can, you if you see this, so you will see that so this angle bit at this 90 plus theta makes the gamma. Okay, so this 90 plus theta makes the gamma. You can see it from this diagram. Okay, so you will see that so this theta can be written as gamma minus 90. So you will see that the expression of torque is given as k into br bs sine gamma. So it is nothing but the torque is proportional to sine of the what you say angle difference between the stator and the rotor mmf. So what will happen? We know that the rotor mmf will try to get as close to the stator. Okay, so because why it will try to do, so first we why it will try to go is, you see, this is because of the Lenz's law. So we will try to see how this Lenz's law is happening. So here, why in the first place this br was coming? Because of the because of this, right? E2 induced. So what is this E2 proportional to? We have seen that this E2 rotating is proportional to ns minus nr. So because of this E2 rotating, there was this current and there was this flux. Okay, so what it will try to do, so in order to what you say, So it will move in this, in that direction, which will oppose the cause. So where will this rotor rotate? It will try to rotate in that direction, which will reduce the cause, which is this E2. Okay. So rotor will try to rotate in a direction which will oppose the cause E2. So it will try to oppose E2. So how it will try to oppose E2? By trying to make it nearly zero. Okay. So if so NR will try to rotate in which direction? It will try to rotate in the direction of, so it will try to reduce this theta. Basically this in the theta it will try to reduce, and it will, this NR will try to approach the speed of this NS. Okay, like that. So this is how this torque is produced. So now we will see some questions. Okay. So let us see the questions again. Now this is the common data for again next 6 questions. So here what we have is, hmm, 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 hmm. No, no. If it is short circuited, then see what will happen is that short circuited means here it is like IR plus IY plus IB. At this place it will become zero. But in these three places, the windings, the current is still flowing, right? And why this current is flowing? First of all, why this three-phase currents distributed in time is flowing? Because of this distribution. This, if you see, these three-phase windings are distributed by 120-degree, right? That is why these currents are also having this 120-degree phase shift. So if suppose you have, if suppose you have only if suppose you have all the core, what you say, one conductor, let us say you have only one conductor. So what will happen? It will be what? So it will not be the 120-degree phase shifted current then. Okay, this 120-degree phase shifted current is coming because we are saying that okay, the rotor windings are also distributed it like how it is distributed here. Here also it is distributed in space. So here we know that, right? If it is distributed in space, then what will happen? Even if you give what you say, even if there is a DC current, this MMF will be what you say sinusoid, right? So like that. Maybe I'll explain it even a bit in a more what you say proper way in the next class. But I think this till this discussion is okay. Okay, if we need to discuss it in more detail, then I'll discuss it maybe in more detail in the next class. Okay. Hmm. But for solving questions, this much discussion is enough. I think this is more than enough. Okay. For seeing these discussions in more detail, maybe you can see sir's lectures. Okay. So, but remember that because of this distribution in space, this 120-degree is coming. Okay. So that is why this 120-degree, that is why this EMF E2 is 120-degree apart. Like this is so here I did that, right? So here if you see, I try to draw this, right? Because of this this MMF, this E2 phase is coming like this, right? So it is like this, that if suppose you have open circuited, like let's say that you have open circuited rotor windings, then what will happen? This E2 will get induced depending on where its position is. Okay. So this is the magnitude or RMS value of this E2, but it will also have a phase, right? Depending on this distribution in space. So because of this distribution in space, this 120-degree thing is coming. So here so this E2 is having E2R, E2Y, E2B depending on the where it is located. Suppose this rotor is locked mechanically, like rotor is not rotating and it is open circuited. So in this case, what will be the E2? It will be nothing but where this rotor winding will have maximum mmf, right? So it corresponding to that, this you will see that this, so this mmf is cutting these windings, and because these windings are distributed in space, that is why this emf is also, what you say, you will see is that it will be, what you say, distributed, right? Huh. So like that. So if you want to see it in more detail, you can see the sir's lectures. Okay. There he has, because see, I'm trying to discuss what sir has discussed it in around 5-6 hours. Okay. So I'm trying to, it's like just cramming the stuff. So it is very difficult to tell this. But sir has taken his time. He has explained it with the, what you said, diagrams, and he has also explained it with moving pictures also. So you can see that. Okay. Hmm. Okay. So now coming back here, now what we have to do is that here, so this is a three-phase two-pole induction motor which is fed from 60 hertz supply. Now this rotor is rotating with 5% slip. Now they are telling to find the speed, first of all, in mechanical degrees per second. Okay, generally when we try to find speed, we find it in rpm, right? Now we will have to convert this rpm to mechanical degrees per second, but as such the question is simple only. Okay, so what we have to do, we have to find the speed of the stator field with respect to an observer stationary on the ground. So what do we know, stator, so what is the speed of the speed of rotating magnetic field in stator? We know that it is what? It is 120 F by P in RPM. This is how it is related to the supply frequency. So let us do that now. So 120 into F, F is 60 by P, P is 2. Okay. So this is how it is. So if we try to find, then what is this? So this is 2 into 30. So this is 3600 RPM. Okay. Now, this is the speed of the rotating magnetic field in stator. But they're not asking the, we know that this is in RPM, but they're asking this question in mechanical degrees per second. Now we have to convert this to mechanical degrees per second. First of all, we will convert this to mechanical radian per second. So mechanical radian per second is 2 pi by 60 into n speed in RPM. Okay, this is the relation between mechanical radian per second and speed in RPM. So if you do that, so you will get speed in mechanical radian per second as 2 pi by 60 into 3600. This will give you in radian per second. But what we have to do, we have to find in mechanical degrees per second. So what is the relation between degree and radian per second? So it is 2 pi by 60 into 3600. We know that, so let us see that. So we have pi radian as 180 degree. So 1 radian is 180 degree by pi. So we have to multiply 1. So here this is 1 radian per second. So 1 radian we have to replace as 180 degree by pi. So it will give you as degrees per second. Okay, like this. So if you do this, so you can just do this 60. So this is this is 60. Then this product of all this 2 into 60 into 180. Okay. So this product you will see, it will come out to be this value only, 21600. Okay. So because this is the original thing, so I just, and so this is how it is coming. Okay. So this is what you are getting in this mechanical degrees per second. So this you have to remember that this is the relation between mechanical radian per second and speed in RPM. Okay, then you can convert from radian to degree, mechanical radian to electrical degrees. Like first you convert from mechanical radian to mechanical degrees, and then if you what you say multiply by pole p by 2, then you will get electrical degree per second, like that. Okay, so this interchanging of units you can do. So this is one conversion, and we know that electrical degrees p by 2 into mechanical degree. Okay. Okay. So these things you have to like remember. Okay. Remember means what? This one you already know. Only you have to remember this one. This one is the new thing, right? This formula. Other things we know. This one we have already seen in the previous classes, and this one we know from our school days. Okay, like that. So this is how you can convert to mechanical degrees per second. Then again they are asking find the speed of the rotor in mechanical degrees per second. Okay, so we know so they have given slip. Okay, so we know that slip is equal to ns minus nr by ns. So ns we know it as what? It we know it as 3600 minus in RPM. First, I'm trying to find in RPM, and then I can convert it to anything, right? So, but I'm trying to finding it in standard RPM. Then I'll convert it to whatever I need. Okay. Then slip is 0.05 into 3600. So this is 3600 minus NR. So this is how much? This is 180, I guess. So NR is 3600 minus 180. This is 0, 2. This is 3520, right? No, 3420. 3420 RPM. So this is in RPM. Then we know how to convert from RPM to mechanical radian per second. So in mechanical radian per second, it is 2 pi by 60 into 3420. Okay, and then mechanical degrees per second is equal to 2 pi by 60 into 3420 into this, right? 180 degree by pi. So 180 degree by pi. So this you will see it is same thing. You will get it as same this whatever value is given. Okay, these are just simple maths. You just have to remember that okay, this is the slip. Okay, we know that okay, speed of the rotating magnetic field is this 120 f by p. These things are very simple. Okay, numericals are very simple once you know these discussions. Okay, now frequency of the EMF induced in the rotor. So what is the frequency of the EMF induced in the rotor? You will see that it will be S times of F, because we saw that, right? What is F2? F2 is because you see here, uh, so let me go here. Okay, so here also you see when we were replacing this, when we are writing it as root 2 pi f pi k omega n1, so instead of f we were writing it as pns by 2. So here you can see that if we write it as root 2 pi f2 phi k omega n2, then you will see that f2 is proportional to ns minus nr. Okay, so you will see that this f2, so I'll just write it here, that F2 is slip times of F1. Okay. So this is the relation between F2 and F1. From that discussion only you can find out. Okay. So here the slip is 0.05 and F1 we know is 60. So 5% of 60 is 3 hertz, like this. Okay. So you will see that E2 rotating is S times of E2 stationary, and F2 is slip times of F1. Okay, these things. So this is slip times of F1, supply frequency. Okay. So now we go to the next question. Now we have to find the speed of the rotor field with respect to the rotor. So you will see that rotor field. So what happens that because this here you see this the stator field is BS and this rotor field is BR. Now, what is BR trying to do? It is trying to move at the same speed as BS, right? Then only so that is how it. So you will see that this rotating magnetic field of BR, it also rotates as the same speed with the rotating magnetic field of the stator. Okay, so you will see that. So I'll write it here. Okay, that. So I'll write down some new things. Okay. First of all, I'll write this that E2 rotating is slip times of E2 stationary. Then F2 is slip times of F1. F1 is supply frequency. F2 is rotor frequency, rotor EMF frequency. Okay. So we know that total EMF frequency is proportional to Ns minus Nr, and then we can replace this as slip times of Ns. And this Ns you can write in terms of frequency, right? So Ns you can write in terms of F1. So that is how it is coming. Okay. So this is how it is coming as slip times of F1. Then this is this. Now another thing is. mm, what else I was writing? Rotor field, about rotor field, right? So rotor field also rotates as the same speed of stator magnetic field, which is Ns. Okay, this is also Ns. So you will see that here they're asking you to find the speed of the rotor field with respect to rotor. So we know that rotor field with respect to stationary observer. Remember that this is all with these things which I have written is NS with respect to stationary observer. Okay, stationary observer. But here they're asking you to find, first of all, we know that the rotor field with respect to stator or stationary observer is ns, and rotor rotor speed with respect to stationary observer is nr. So they're asking you to find ns minus nr. Okay. If they would have asked you to find the speed of the rotor field with respect to stationary observer, with respect to stator like that, then it would have been ns. But because they're asking you to find the relative speed, because rotor is also rotating at nr, remember, right? So what will be the relative speed between the rotor field or stator field? It could have been stator field also. Stator field with respect to rotor, then it would have been ns minus nr. Okay. So this ns minus nr you can find in rpm. So 3600 minus what you say nr is what? Nr we have found out here, right? So nr is 3420. Okay, this is 180. So this 180 is in RPM. This you can convert to mechanical degrees per second as per our discussion here. Okay, this you can do. This I have discussed it two times. So I guess, I hope you understood this. You just have to remember this. Okay, 2 pi by 16 to n RPM will give you mechanical radian per second. And then from mechanical radian per second, you can go to mechanical degree or electrical degree by using these conversions. Okay. So this is the thing. Now they're asking you to find the speed of the rotor field with respect to the stationary observer on the ground. This is what I was saying, right? With respect to stationary. So the rotor field with respect to stationary observer is ns. Okay, so this is just ns. So this is ns. So we have found ns already, right? Which is the, what was the first question in this series? So the first question was find the speed of the stator field with respect to an observer stationary on the ground. Okay, so that this is how it was. So with respect to stationary observer, stator field and rotor field is both ns, but if it is with respect to the rotor, then it is ns minus nr. Okay, like that. So here you can also again find ns and rpm and then convert it to ns. So you can convert it to electrical or mechanical degrees per second. This conversion we know how to do. Okay. And then in the last question, at what speed this motor would run under absolute no load? So at no load, NR is approximately equal to NS. Okay, this is the situation. So you will see that it is approximately equal to NS. Okay, so that is because slip is nearly zero. So if you see the torque versus slip characteristics, so you will see that at no, so you can find like that at no load the slip is nearly what you say zero. Okay, like that. So this you just remember. This I will discuss it more in the next class. Okay, that at no load the nr is approximately equal to ns. Okay, so I know there were many things in these things. Just try to see these things. This like as I have discussed it in the sequence. Then I guess you will understand what all things were happening, how the induction motor actually rotates. These things you know, and then you should know these things that okay, what is the frequency of the induced EMF? What is the value of the induced EMF in the rotor? Then how this what is the speed of the rotor magnetic field and stator magnetic field? These things only is enough to solve all the questions. Okay, so and you just have to remember these conversion formulas, that what is the relation between mechanical radian per second in r to the rpm, then what is the relation between electrical degree and mechanical degree, what is the relation between radian and degree, like this. Okay, so these things you, if you know, then I think you can solve the questions for this kind of assignments. Okay, this assignment specifically. So that is all. So I'm stopping the class here today, and we will maybe discuss it more things maybe on this where it is. So let me just tell you. So here we may continue from here. I will maybe discuss why at no load this is nearly the NS. Okay. So with this we can just start our discussion. So, so that is it. So, is there any doubt anywhere? I know there were many things which I have discussed. So, just please try to see these things. And for getting more clarity, you can also see the sir's lectures because sir has discussed it in lot of details. So, you can try to follow sir's lectures. Okay, for more theory. Okay, okay. Thank you, Shiv Kumar. Then, so thank you everyone. If there is no doubt, then I'm stopping the class here today. Solving questions is very easy, okay? But th for solving the theoretical questions, you have to know these things, okay? These things you have to know. Then you have to know these things like this. And in the beginning, we have seen this discussion, what you say, this discussion about the rotating magnetic field, okay? And how to find resultant mmf, so these things. Okay, so I'm stopping the class here today. So that is all. So thank you everyone. I'm leaving. Okay. So okay, okay, then thank you Abhitesh. Okay. Okay, bye.